So today we're presented with a problem. And the problem is we have some bar here of some material with a constant diffusivity. So it has a constant thermal diffusivity, which is a measure of how the heat travels or propagates through this bar of some material. So let's start off by saying that we are interested in one of these little slivers here. So let's say this sliver here has some temperature, and we'll call this J, just as a counting thing. So these are equally spaced little widths here. So we can give them some standard width measurement. I'll call it delta x, as well as having a constant cross-sectional area. So I'll leave that as A. So when we're talking about temperature differences throughout this bar, we can look at its neighboring little wedges here. So we have temperature of this J plus 1 wedge, and then a temperature of this J minus 1 wedge. So if we were to say that the heat is propagating from the right to the left, let's say we have some heating element here, our heat would propagate from this sliver all the way down until this entire bar reaches a steady state, which is to say that the entire bar is at a uniform constant temperature. So the easiest way to start tackling this problem and modeling this heat travel is through an energy balance. So I'll start off by looking at this differential temperature, or this change in temperature with respect to time. Now, units of this are something like maybe Celsius or kelvins per second, some temperature per time type ordeal. So I can bring in the specific heat of this material, and this will convert it. So if we did it this way, specific heat has maybe, so like, let's just use standard. So joules per grams Kelvin, right? And then a temperature per time, so Kelvin per seconds. Canceling out these Ks, we have something like in the joule per gram times second realm, something like that. Our target is maybe some joules per second type arrangement. So let's keep going. I know that if I want to cancel out that grams term, I can use my density of this material, not a triangle, a density of this material times its volume. Because if we do a dimensional analysis on this, so say we have grams per meters cubed times meters cubed, well, of course these cancel. We just left with grams, we get that mass term out of the way. So I can multiply my density, and the volume of one of these little slivers here is this delta x times A. So let's add that in too. So delta x A, and this counts as our velocity term, our volume term, not velocity term. Now the other side of this, we can use a very common law in heat transfer, which is known as Fourier's law. Fourier's law, which states that this heat rate is equal to minus K, the thermal conductivity, area, which is the cross-sectional heat transfer area, dt dx, this temperature over a differential width. So the length over which you are concerned about this heat transfer. And that will fit in very nicely with the rest of our energy balance here. So let's go ahead and do that. So minus Ka, notice we have cross-sectional area on both of these sides. And let's say that our heat is propagating from the right to the left. So when that happens, we'll have a higher Tj plus 1, and we'll calculate that temperature difference by subtracting its neighboring sliver. And this is over delta x. So this is, if we talk like, say, center to center, so we're worried about the center of that, of this sliver, center of this sliver, this should still come out to be around delta x. So we'll just use that assumption and create our energy balance. So another thing we can do, so we already said that if our heat transfer is going from our right edge towards our sliver of interest, we get some sort of Fourier's thing like this. But we can also have heat transfer coming from the other side. And that will have the same thermal conductivity, that'll have the same cross-sectional area. So what we can end up doing, with the right color of course, is say, well, we can add on this term from the left. We'll say Tj minus 1 minus Tj over delta x, which is, again, the same. And this accounts for heat transfer on almost, kind of like heat transfer on both ends of this bar. So that's kind of cool. Now, we talked about the thermal diffusivity a little bit. So this alpha, well, this alpha really is just equal to rho c, actually, well, the opposite, so the inverse, k over rho c. And what we have over here, if we divide this over, is actually the inverse of that. So we can rewrite this to say, so delta xa over alpha times dtj over dt equals its cross-sectional area, tj plus 1 minus tj over delta x plus tj minus 1 minus tj over delta x. Now, I want to pay attention to this term here. Now what we're going to do is we're going to discretize this, take it from this differential form, actually use discrete time intervals and discrete temperatures to allow us to almost average this. It'll make a bit more sense when I actually write it out. So let's do it maybe in this blue color, right? So this differential here, we are essentially saying that as time progresses, our temperature of our sliver of interest will change over time. Which is to say that if we have some temperature at some time n plus 1, let's say, that's going to have a higher temperature than its original state. And we analyze this change over some selected range of time. So now we have transformed this differential into something that can be algebraically construed. So I'm actually going to plug that in, as well as canceling out these cross-sectional areas, because essentially they're not going to help us. And we also realize that we have common denominator here. So when we do this, we're actually going to get a very, I guess, a really algebraically solid answer for us to be able to analyze. So delta x over that times tjn plus 1 minus tjn over delta t equals, and now let's write it out. So now we have tj plus 1 minus 2 tj and then plus tj minus 1 all over delta x. So that's pretty good. Now the last thing that we can do is kind of collect all of our delta x, delta t, alpha terms, kind of collect it all in this little box here. So let's do that. So we have delta x squared, so we're going to multiply both sides, over alpha delta t times this discretization that we had done earlier equals tj plus 1, and this is at time n, minus 2tj time n plus tj minus 1 at time n. Now the last thing to do is to isolate this term, because this is actually what we are interested in. We're essentially trying to analyze this change of this little sliver as time progresses and as our temperature propagates through our bar. So let's just isolate this term. Right? So first we can divide both sides by this. So let's do that. Tj n plus 1. It should be a minus. I don't know how that got turned to a plus. Equals, so alpha delta t over delta x squared times our big long temperature chain here. And then we just have to add this tjn over, so I'm actually just going to do that right here. And then get rid of that here. tj sub or tj super n plus that. And this is an algebraic expression we can use to analyze the temperature profile of our bar as it navigates through time. So now let's use Python to kind of model our situation here and kind of develop this temperature profile as it goes through time. So coming back here, I kind of want to condense maybe this little term here into just one term that I can kind of change according to how I want it to. So I'm going to call this R, and we will also code that into Python. So let's just start doing that. So our initial state here is that our bar is at a uniform 20 degrees Celsius, and at time equals 0, one end is heated to 50 degrees Celsius and the other end is heated to 80 degrees Celsius. And our goal is to see how that temperature propagates and eventually reach a steady state after some time has elapsed, and then kind of figuring out at what time period does that steady state kind of show itself. So let's go through the motions here now. So I'll start off by defining our alpha. So our alpha right now I'll just set for 1. It is constant throughout our entire process, so we do need to actually explicitly state what that is. It's not going to be some function of maybe some other variables. It's something that we can control about our material. We have a dx, so we can set that to whatever we want, maybe like 0.5 meters, doesn't really matter. And then we have a dt, so whatever time interval we want. And that should be all we need to find our R. So that's alpha times delta t over delta x squared. So let's do that. So alpha times delta t, put this in parentheses, over delta x squared. So now if we check our R out, yeah, it's a value that we are able to modify by adjusting these parameters just a little bit. I also probably want to state how many discretizations, how many slivers of my bar I want to work with. The more that I get, the more smooth of a gradient I will see, and when I actually plot out the different temperature profiles at different times, it'll be a much smoother curve. So I'll probably go with something like n equals maybe like 100. Right now I'll stick with 10 just so when we do set up this array for which we can actually see our temperature numbers changing. So maybe let's set up, so this T is going to be for my temperature profile, and we're going to set that to a full array equal to the amount of different values that we want, and the initial value. Right? So now, boom, I have a full array of 10 20s. And at time equals 0. So temperature at, so I'm going to change this first position. So here's the thing about the little numbering. At T0, I'll go equal to 50. So now you see, this is considered our 0 position. But in our problem statement, we said that both of these sides start with some initial, or I guess not initial condition, but a condition at time equals 0. So how we are able to change that n value, that, wrong brackets, we use a -1. And this basically says, well, we've got to set it equal to something, so 80. This basically says whatever that n value is, we want to change that. So the last value in that array lines up with -1. And that counting starts backwards. So this is -1, this is -2, this is -3, this is 0, 1, 2, 3. So that's just kind of how the syntax in Python kind of works out. So I'm going to increase this to the desired amount of discretizations that I actually want, which is 100, which will give us a much nicer and smoother graph when we actually go through this entire derivation in Python. Now the next step is going to be taking this array, these initial values, and using our energy balance to populate those values in the middle of our array, and eventually, as time changes, be able to plot out that each temperature profile at each difference in time, which we can set up here. So now we've created this array, and that's all fine and dandy. But now, how do we kind of update those values to match start creating temperature profiles that lead to our final steady state? So in Python indexing, if we were to say T1:-1, we see that this first 50, that's actually, so let me put T here. So this first 50 is not there, so that position 1, but actually this also ending 80, which actually we defined that as -1 earlier, is actually excluded in the indexing. So it goes from this term to this term -1. So really what it's showing us is 1 to position -2. So what we can say is that we can update this array now. Get rid of this. Is equal to that T from 1 to -1. And then plus our R times So now, going back to here, first we want to look at our j plus 1, which is everything from going on from here to the end. Well, I guess it really does depend on which one you consider to be j plus 1 or j minus 1, but let's just follow this. Let's just follow this example here. So we get r times, so that tj plus 1. So that's going to be from our t array. We go colon 2. Right? So that picks up everything up until position 2. And then minus 2 tj. So that is what's in our middle. So minus 2 times t from 1 to minus 1. Right? And then plus our t 2 colon. I think I got my order mixed up a little bit. This should be from there, from position 0 to minus 2. And this should be from, right? Okay. I think maybe now we're good. So let's see what that looks like now. So now we see that these end temperatures are slightly now raised compared to all these values in the middle. So that temperature difference is now starting to kind of show, it's starting to evolve through our bar, and that's the representation that we have here. So by now you probably realize that if we're going to do this over and over and over again and collect a multitude of different temperature profiles, we need to assign an array to kind of collect these profiles, and then later we're going to be wanting to plot them. So I'm going to save a copy of this array into a new array called our temperature profiles. And I'm going to create a for loop here. So for I in range, how many time intervals do you want? Let's set with 100 right now. Right? We're going to calculate this. It's going to change up our array. It's going to develop a new temperature profile for us to analyze. And we're going to append it to our temperature profile. So put another copy of that right there. Now, if we do this 100 times, let's just take a look at our final temperature profile here. So now we see that we're pretty much almost at a steady state. That could very well just be a straight line. So all things considered, that's looking pretty good. So now we're going to set up a new subplot. And basically every single time we go through this this loop, we're going to use a counter. So we're going to say for k in tprof here, right? We're going to add a scatter, right? Our x is going to be equal to our position. So we want to have each position plotted out. So we have 100 positions. We're going to go np.arange n. And what this does, I'm just going to probably do this. Let me just show you. np, let me just copy and paste it from here. See? It just gives you each integer in that counting. Right? So we're going to set that for our x values. so that we have all our positions there. And our y values are going to be our individual values in our profile. So I believe I could just do that. Let's see if that terminates properly and gives us a result. Okay, slight mistake. It should not have been the T, because that means that it's trying to put that entire array. What we really want is to use that counter to allow us to pluck out each one of those arrays and put that into its own graph. So now if we do it, there we go. We see that the temperature starts propagating with time. Maybe we don't want to see so many of these at one time. So what we'll do is we'll do something like, or I think it might be actually maybe like every 20. Yeah, maybe right now we'll just go every 10. But basically we see this initial steady state, right? We have the initial heating that we see at position 0. Position 1 shows 20, and eventually over time we see this start to propagate out. Let's see, maybe 200 of these. Right, see now we're starting to broaden out, maybe like 1,000, and I'll change how many we see, so maybe 100, maybe not that much, maybe like 50. Even then, that's not too many. But yeah, you see now we're starting to reach that steady state. So let's see what happens when we get maybe like, whoa, right, we definitely need to see less of that. Here we go. We see that by the time we reach up here, we actually do approach this pretty nice steady state that we have. It's about that straight line from position 0 to position 100. And we see that it's nearly a straight line as we trace along. So maybe we don't need 10,000. Maybe the real actual time that actually it hits steady state is somewhere less than that, but you know, not bad. So we've finally developed this nice little plot that allows us to visualize these temperature profiles as we reach a final steady state. But something that we can also be interested in is we have an R value up here that we have calculated using some defined values. But there is an analysis that we can do based on this R value and the stability of our solution. So to make that point, I'm going to start off by changing our R value to 0.499. As you can see, we still have a pretty nice plot. Everything still is pretty cohesive, pretty easy to understand. However, it's when we cross this 0.5 boundary, so maybe like 0.503, something small, I guess. We see now our nice graph has developed this oscillatory behavior that is complete nonsense. We can't gather anything from this chart. However, nothing here has changed. In fact, the only thing that's changed is this R value, which is why it's so crucial to actually choose these values precisely. Otherwise, you get kind of mumbo-jumbo answers. And that is something that can be, I guess, explained through something called a von Neumann analysis. So what I mean by that is our thermal diffusion follows some partial differential equation here that looks like this. So we have this partial of our temperature with respect to time equals to our thermal diffusion constant times the second partial derivative of temperature with respect to our x, our position, I would guess. Now, looking at this, our goal is to kind of prove the stability of our R value and how that affects, or I guess what governs that sort of behavior. So we can start off by saying, well, a partial differential equation like this might have some solution that looks like this. So minus alpha k squared t for time times e to the I k x. Now, you might look at this and wonder, well, where are these values coming from? And I think a better way to visualize this is proving how this is actually a solution of this differential equation. So let's start on this side first. We can say, so this derivative of temperature respect to time. So we know that with exponentials, we have some general form like this. If we take derivative of this with respect to x equals something like that, follows this general form. And it's this kind of function of keeping its identity that is, I guess, sort of, that is something that we like, something that we want to keep in our general solution. So we can say this exponential in regards to its time dependence, there's nothing going on there, so that stays constant. And so what we end up having is minus alpha k squared times e to the minus a k squared t times e to the I k x. We recognize that this still is t. So our derivative looks something like that. Now, for our second derivative, so this one right here, quite literally a second derivative, we can first take that first derivative. So maybe let's start like that. We'll take the first derivative, and that is equal to I k t, because like last time, this e will stay and that will regain its identity. And its second derivative is just the derivative of this again. That's I squared k squared t. I squared is just equal to the square root of -1 squared, which is equal to -1. So this equals minus k squared t. Now, let's go back to our initial partial differential equation. So if we plug that in, we get minus a k squared t, or I guess minus alpha a k squared t equals alpha times minus k squared t. So we see that these two sides are equal to each other. So now that we proved that this solution here for our temperature is indeed a solution of our partial differential equation, what I now want to do is kind of add that time dependence back in there. So let me rewrite this out here. So e minus alpha k squared t e to the I k x. Wrong t, this is time. So if we were to say that this t is specified for some time and some position j, we can add that discretization into our exponents here. So that looks something like this, k squared times n delta t. And that adds this time difference, so some discretization of that time, some time range, into this expression. And the same happens for our positioning, so I, k times j delta x. So that looks pretty good. Now remember that when we derived this overall equation, we have some j plus 1 and j minus 1 for some time n. So if we were to rewrite this for those, we'll start with minus 1. So we get e minus alpha k squared n delta t times e to the I k j minus 1 delta x. And what we know about exponents like this is that we have a subtraction of exponents. So we can actually pull out. So let me write this out maybe, just so it makes a bit more sense. N delta t. So this is equal to e to the I. Let's go this way. I k j delta x minus I k delta x. Now recognize that this here is just equal to tj at time n. So of what we really get is an expression that looks like this. So we can actually do that for our j plus 1 too. So t and j plus 1 is equal to tj n, and this is e to the positive ik delta x. So what we do now is I want to rewrite this side of the expression, but I'm going to pull out this tj n term. So actually I'm going to just do this here. Why not? So tj n plus 1 is equal to tj n 1 plus r. And basically now we're going to be pulling tjn out from this expression and this expression here. So for the j plus 1, that leaves us with e to the positive ik delta x minus 2, and then plus e to the minus ik delta x. Right? So that's pretty good. Now, what we have to say is we need to set some boundaries on this. So what exactly do we mean by that? Well, we know that this r is some constant defined by our parameters. So this magnitude over here multiplied by whatever's outside cannot be more than 1, or else our tj for n plus 1 as our time progresses is going to slowly start reaching infinity, and we will start getting oscillations kind of like this. So that's where this analysis will go next. So we can actually use Euler's identity to kind of simplify this down for us a little bit. So e to the ik delta x. So if we have a general form e to the ix, that's equal to cosine x plus I sine x. This is a general form for Euler's identity, right? So if you write this out for I to the k delta x, This is cosine of k delta x plus I sine k delta x. For e to the minus I k delta x, this minus kind of carries over into this k delta x over here. And so what we get, actually, our cosine will stay, our cosine will stay like this, but what will end up happening is this sign will get flipped because we take this, to take the minus out into here. And so now what we find is that these two sine terms will actually cancel out, and our result, oh boy, our result is actually these cosine terms that add up. So we can actually go ahead and rewrite this term like so. So 1 plus r 2 cosine k delta x minus 2. So we were able to use Euler's identity to help us kind of contain this equation. And now we see a little bit more about what I mean by amplitude. We see that we now have a wave function, a cosine function. And what we end up wanting to have is we want to bound this function. I'm going to use a different color actually. I want to bound this function between minus 1 and 1. So either we have an amplitude that overall decreases or an amplitude that overall increases to a certain bound. So we can set up an inequality. So minus 1 less than or equal to 1 plus r 2 cosine k delta x minus 2. And so we have this inequality that allows us to kind of manipulate our cosine and our r to allow us to kind of bound our r to some value. So let's just go ahead and start doing what we can algebraically. So we're going to subtract 1 on both sides. So minus 2 r 2 cosine k delta x minus 2, 0. Now, we know that there are two extremes for cosine. We either have cosine 0 is 1 or cosine pi is minus 1. So we can, what's the best way to go about this? I think we set this equal to pi and we'll get an extreme there. R, if we set this to pi, cosine equals minus 1. So actually we get minus 2r, right? No, let's just keep it like this. R times minus 2 minus 2, right? If we do a cosine pi, minus 1. And I think you can see where this is going now. So minus 2 is equal to minus 4. Divide over to this side, we get that our r has to be less than or equal to 2 fourths equals 0.5. And that is exactly what we saw over here. We can set this equal to 0.5 without any problems. We still get nice and readable graphs. But the second we cross over that, a whole lot of black magic happens and we're not able to interpret our results anymore. So that's kind of the analysis and the reasoning behind why we have bounded it as such. And now we have in detail described how we can model the propagation of temperature diffusion across a bar with a constant thermal diffusivity, as well as the analysis that allows us to calculate the bounding for our R coefficient.